while more people are joining in, while we're 16 participants right now. All right, so the plan is the following. We have lab 10 to finish. Yes, Jana, I hear you for today. And it is actually our final lab for this semester, which means we're not gonna meet anymore as live sessions or synchronous classes, but definitely we can meet one-to-one if you need us to. And probably if we have time, we can do a review session or so on. But I think you need time to finalize your lab reports, and I need to sit and correct all of them, okay? Or most of them before the final exam. For your class, I'm so behind. For other classes, I'm more on time. I don't know the reason, probably the number of students or practically the day and the time. Do you have any comments, any questions, anything you want to add before we start lab 10? Yeah? You're good? I'm gonna take your silence to be a positive signal. Oh yeah, thank you so much. You need to talk about the final. Thank you for reminding me. So far, other sections are fighting for Monday, May 10. Monday, May 10, which is the last day of the semester. And I don't like this. However, I realized that it could be the best option. My class this morning asked for to make it at 5 p.m. For many reasons. Somebody was busy before that, but they don't want it to be really late. So what do you think of Monday, May 10 at 5? I wanted it earlier, like during the week, and then I realized you told me, I don't know who told me actually, that you have so many exams the week before. So you're good with it? Shall I publish this with the other sections, with the other instructors, so we can have a confirmation? And if we do confirm it, we can post it on your calendar, so now you can at least focus and organize your time, and I like this. So Monday, May 10 at 5 p.m. I'm gonna share it on the WhatsApp group because I did not have the chance to meet with my other students of Monday yesterday, so probably they have something. Also, I assume the last day you don't have classes, so 5 p.m. could be okay. Anybody has a class after 5? I have a class at 6. I can postpone it like for a few minutes. Fair enough. All right, I'm gonna keep that on our slide, and let me save as so I can keep it somewhere. Otherwise, I would totally forget about it. Yeah. May 4, we don't have Physics 301. What do you mean? The test? Okay. Carl is advertising for May 4. What is May 4? Let me check. May 4, and let me go to month. May 4 is, yeah, May 4 is a Tuesday. What do you think? So initially you had something on May 4. Okay, question for Carl. Carl, is May 10 bad for you? All right. Anyway, I'm going to keep your request in mind. Probably write it down, May 4 question mark. Keep it just in case. But I know for a fact it's not going to happen. Okay. Suggestion from Carl. All right. Okay. So we will get back to this week. I'm not going to wait until next week. This week, so you can have it somewhere on your calendar. I don't know, Roy. Let me check the WhatsApp group. Yesterday, Imad asked for, is Imad with us? Well, Imad is in the Monday group. Okay, let me find your class. I did not talk to you today. Your class. Come on, Jessie, come on. Yes. So, Imad was requesting to postpone it till Saturday. So Saturday is the new date. Okay. All right, Jana. So Saturday is the new date. Saturday is in few days after today, the first Saturday from today. Okay. You're talking about the deadline for Lab 9. All right, so I'm gonna type here deadline for lab 9 was moved to Saturday. That's the deadline for lab 9. Now final exam in physics lab most probably will happen Monday, May 10. Okay, any issue? At 5 p.m. Yes. Okay, I'm glad this is clear for everyone. Please let me know if you have any issue. I'm ready to modify anything for you. The point is for you to do well, and not the point is to overwhelm you. I know sometimes you need a structure, you know, otherwise it's gonna be chaos with no structure. Trust me, personally, I can't work without a structure. All right, so I'm gonna start with specific heat of a metal. Do you remember what was lab 9 about? Lab 9, what was it about? Anyone? Unmute or type in the chat. Lab 9, title, idea. Linear expansion. Thank you. And by lab 9, I was discussing how water is exceptional, the way it undergoes linear expansion, especially at 4 degrees C. Again, I'm going to discuss water because water has an interesting specific heat capacity. It is a very high specific heat capacity, and it has a lot of consequences. Before I move on, the outline would be what is the definition of specific heat capacity? How do we reach thermal equilibrium? Why, how, and how to calculate the final temperature? The experiment, and the experiment is about thermal equilibrium, and the lab report, how it looks like. This is my first thought, relating water to sand. And I know for a fact that water remains cold or cool throughout summer, and you know this. It heats up definitely, but not as fast as how much sand is actually heating up. Do you have any experience on that level? So Maria is saying that water as an H2O needs a lot of heat to evaporate. That's so true. But I'm talking about H2O in a liquid state and how we can heat it from, let's say, from 20 degrees C to 37 degrees C. If you touch the sand or you step on the sand, it's going to be boiling hot, you know? But if you put your foot in the water, it's not going to have the same temperature. Water takes so much time to heat up. Any consequence on your life? Anything ever happened to you regarding the fact that water needs time to heat up?
When we go to the beach, the sand would be very hot, and when we get in the water, we feel relieved.
Yeah. Did you ever swim? Did you ever swim in the fall or in the spring? I don't know if you swim in the sea, because I heard from the other section they only go to the pool. They hate the sea, they're too scared. I'm talking about a very small group, and it was funny. Do you swim in the sea? Because I do. And the water temperature affects me a lot. I hate cold water. Do you swim in the sea? Did you ever swim in April? April is this month. I'm sure you went to the beach this weekend. It was very high temperature and the weather was nice. Did you go to the beach? I cannot say that I know you're overwhelmed with studies. I'm really sorry yeah, I know. I'm so sorry for that example. I feel bad already. Anybody do you guys go to the beach in November? Anybody ever swim in December? Never. All right, I'm gonna show you something. So this is the water temperature here in the Mediterranean, and those are real values. I don't know which year is this, and I'm not very sure that they're gonna vary a bit throughout the years. But the interesting part is that the temperature in April is so much colder than the temperature in December. And this is cool because, you know, in April you can be in short sleeves, and yet the water temperature, anything below 20 is really so difficult on the human body, depending. Definitely it depends if you get used to it or not. I swam once in a temperature of 13 degrees C. I could barely breathe. I swam once in May. It was around 20 and it was really cold. December was so good. I did one swim in December and it was really okay, you know? And can you tell me the reason why? April is a warm month. How come the water temperature is so low? However, December, you're usually in jackets and you are usually cold. You cannot remove your t-shirt easily. How come the water temperature in December is still too low, too high? Any thoughts? All right, so Marilyn is saying it conserves the heat. It is a heat regulator due to many other things. Anything else? Any other reason? Any other thought? Water needs a lot of heat to raise its temperature. Thank you, Ali. And a lot of heat to be removed from it. It takes longer to heat in April. In general, it takes longer to heat and longer to cool down. Unlike outside environment, it heats up quickly and it cools down much quicker. And this is due to the specific heat capacity of water that is actually high. I need to add something that I did not mention in my previous section. You need to add to this that snow is melting in the spring and it adds up a lot of cold inside the sea. And this is like I was cheating, I did not mention this. That's why spring season is usually very low because snow is melting. So this adds up to your problem. Anyway, I'm gonna start discussing specific heat capacity of any substance. By definition, do you know what is specific heat capacity and how is it related to the fact that it takes longer to heat and longer to cool down? And probably you can use Ali's intervention. Water needs a lot of heat in order to raise its temperature. So what is specific heat capacity? Anyone will give it a try? Specific heat capacity of any substance. How do you define it? You can use Romi's intervention and Ali's intervention in the chat. So specific heat capacity is
the amount of energy that it takes to heat 1 kilogram of water by 1 degree Celsius.
Perfect. And Ali is saying amount of heat needed to raise a specific mass of water. I'm going to say a unit mass, like 1 gram or 1 kilogram by 1 degree. All right. This is exactly what you need to know. So very simple. Highlight. So it's the amount of heat required to raise the temperature of 1 kilogram by 1 Kelvin. Okay, so you can see here that you have the mass needed. You can use that to be in kilograms. This could be in a Kelvin, and this could be in joules or in kilojoules, anything you want. And you can find C easily. And the unit of C would be, what would be the unit of C? Kelvin, something is missing. Isn't C Q over M delta T? So what would be the unit of C? It's the amount of heat needed per mass and jump in temperature. Yes, thank you so much. So it's gonna be, in this case, joules times kilogram to the -1 or divided by kilogram divided by Kelvin to the -1. All right, now talking of Kelvin a bit, how do you convert temperature degree C into Kelvin? Do you plus or minus or multiply or divide? All right, so it is plus 273.15 if you want more significant figure to convert from Celsius to Kelvin. Now, if I have a raise of 1 Kelvin, how many degrees C is this? So if the temperature of my water in this cup has been raised by 1 Kelvin, how many degrees C this one has been raised? It's hot, I can assume 60 degrees. So if the raise is 1K, how many degrees C is that? You add 273, you minus 273. Jana is saying it's gonna be the same. So Jana is saying the change in temperature, if I take it in Kelvin or in degree C, it's gonna be the same. And I totally agree. We don't plus 273, we don't minus 273, we're talking about the jump in temperature. So if you have a temperature of 37 degrees, it jumps to 38, that's a plus 1 degree C. If you convert each to Kelvin and find the jump, it's gonna be 1 Kelvin, which means if you use delta T to be in Kelvin or in degree C, it's gonna be the same. And if you have C in joules per kilogram per Kelvin or joules per kilogram per degree C, it's gonna be also the same. Do you agree with that? So we're not talking about temperature conversion, we're talking about the raise in temperature, and that's not T, it's delta T. Do I make sense? Yes, do I make sense? All right. So here you are given some specific heat capacity. You see the unit joules per gram per degree C, and that's okay as well. Can you find which substance has the highest and which substance has the lowest specific heat capacity? All right, so water takes a lot of joules. You need 4 joules, and 4 joules is a lot, to raise the temperature of 1 gram by 1 degree C. And the lowest is silver. I don't have any experience at home with silver, trying to heat up silver. Probably some experience with aluminum, because you have aluminum around the house, and usually when you touch aluminum, the touch is cool. I don't know. Anyway, can you think of other applications for water? So water having a very high specific heat capacity, it has a lot of consequences in your life. So one, the temperature of the sea versus sand. Two, to heat up the water of your coffee, it takes a lot of time. However, if you heat up a spoon, it takes a second to be really boiling hot. Can you think of a third alternative? Third consequence in your daily life because of high specific heat capacity of water? I can think of something that is very important and vital that I would love to discuss with you. It has a lot of biology. Minimizes changes in temperature. How, Maria? Please explain and teach me. I don't know this. Okay, sweating is about evaporation. So yes, sweat on your skin helps to regulate your temperature, but it has nothing to do with specific heat capacity. However, I'm thinking about something very close, Ali. Any thoughts? Something vital because of specific heat capacity of water. Yes, water in our bodies. What happens because of high specific heat capacity? We don't heat up and we don't cool down easily, right? And this is good. Otherwise, yeah, exactly, Jana. So we're not affected by temperature as much, and people that are dehydrated usually are affected more. So water is very important for us. By the way, I believe this example is also good. They're talking about Lake Michigan and how it takes longer to heat up and longer to cool down, and how some countries, some towns that are locked down, surrounded by certain lakes, they're actually affected by warmer winters and cooler summers. So it affects the ecosystem and the body, the human body temperature. You know more than me, but keep that in mind because there's a question in the lab report related to the fact how high specific heat capacity of water can affect or has consequences in your daily life, okay? So for you to be able to find the heat added to the system, you do MC delta T. So M is the mass of your system, sample, C is the specific heat capacity of your sample, and delta T is the temperature jump or temperature increase. I'm going to take this as a general example, H2O. This is the graph of temperature versus heat or time, because you need time to heat it up. It's a continuous supply of heat. So somehow they're proportional. Isn't heat power over time? Power over time, yes, it is. Heat is energy. So temperature, I need help at regular pressure. What is the temperature of melted ice or ice melting? Because this is a sketch, and if I can add some values to my sketch, it would make more sense. So temperature of melting ice with unit, please. The temperature of melting ice, it's gonna be 0 and the unit is... Thank you, Carl, for being a nerd by saying 273. I wanted to say the same. Maria, back to you. You said degree C. All right. And Carl is saying 273 Kelvin. Yes, cheers for that. Now, what's the temperature of water and steam? All right, 100 degrees C. Thank you for adding a unit. Okay, so as you can see that sometimes the temperature does not increase, and this is very important. Here you have a temperature increase. Here you have a temperature increase, and here you have a temperature increase. However, in this case, you don't have a temperature increase, no temperature increase, because all the heat would go into changing the state. So you either have a temperature increase or a change of phase. You cannot have both at the same time, and they happen in steps, you know, one step at a time. If I take this case, like here, change in temperature, the heat added will contribute to MC delta T. Okay, knowing the mass of the water, the specific heat capacity of water, that I'm gonna say CW, called CW, delta T is the change in temperature. I can calculate the heat added, and it's gonna be the difference between point A and point B, because point A and point B, the difference is how much heat you're adding to your system. If I assume the x-axis to be heat or Q. And same thing here, I'm gonna do MC delta T. However, I need to take C of vapor because it's different than C of liquid water, even if it's the same sample, which is H2O. And same thing here for ice, it's gonna be M C of ice times delta T. And yes, trust me, C of ice is different than C of water. And the last team were asking me about it. Look, C of ice is approximately half than the C of water. So water would heat up or raise its temperature so much faster, like double the time, than water itself. Yeah, it's weird. We're talking about H2O. However, do you remember how to find why? I think it's related to the composition of ice. So it has nothing to do with H2O. It's how ice itself behaves. So let's say you have ice at negative 20 degrees C, and you want to have ice at 0 degrees C, and you want to heat it up. It absorbs temperature faster because of what it is, you know? I don't know, probably there is a very easy answer to your question, but for me, it's just, this is how it is, and this is how it behaves. Why do you think water needs more heat to increase its temperature? Because this is how it is. Okay? Could it be responsible for a specific bonding? I don't know. Probably you can ask the chemist for that, but I think this is a fact, you know? Related to what exactly, I don't know what is the answer to your question, Jana. However, your question is very interesting. So now I cannot use density of ice. Why do you think it's related to density? So temperature increase. We're talking about the same mass. It's only that it has a bigger volume, right? It has a bigger volume. And how does this affect temperature? I don't know. Probably, Jana, it's related to the hydrogen bonding. I don't know. But I don't think geometry of the molecule, Maria, Roy, we're talking about the same mass. Probably the geometry of the molecule has something to do with how much heat it's absorbing. I don't know. I don't know. We can read about it. I really don't know. I never thought about it. Now my question for you is, I can use MC delta T for change in temperature, but I cannot use MC delta T for change in phase. Do you remember from high school? Because I heard from the other section that you did not do this in the course yet. How do you find, you know, there's a heat added to your system and a lot of heat. And here you have even more heat added to the system to change the phase from ice to water or from water to vapor. How do you calculate the heat added? Especially that you don't have an increase in temperature. How do you find this? Anyone remembers? Yes? So, can you remember? You can say we forgot. Just answer my question. I need to know if you can hear me. Anyone remembers how to find the heat? Like for example, if I have an ice cube, Jana, and I need to heat it up, and I want all of it to melt, how much joules should I give to my system? That's the question. It is obviously related to the mass of the ice. The bigger the ice cube, the more heat it needs. Anything else? It's not MC delta T, because it has nothing to do with the change in temperature. The temperature is not going to change. All of the ice is going to melt and the temperature is going to remain 0. Anyone knows how to find Q? Yes, you took it before. You know it from back to, I don't know, grade 8. You should know it. So, and you can't remember. So basically you need to use the latent heat. Does it ring a bell? Latent heat? Carl? Nothing? Okay, latent heat is the heat needed to change the phase per kilogram. Okay, so simply to find Q, you do M times the latent heat. And latent heat is related to like H2O has a specific latent heat of fusion, and fusion means melting. And it has a specific latent heat for vaporization, and vaporization means evaporation. Okay, and latent heat for vaporization of H2O is really, really high. That's why in this state, it's very dangerous to touch, because we're talking about values beyond 10 to the 6 joules, you know? So, and as you can see, this is usually long and this is not up to scale. Otherwise, it's going to be longer. I think I have some values to show you. Let me see if I find the latent heat water. The one for fusion, I mean fusion melting, it's 334 kilojoules, or 334 and 3 zeros. However, for vaporization, it's 2 and 6 zeros, because you have kilo in here. You see, it's really big. We're talking 2 million something joules to heat, to be able to evaporate 1 kilogram of water. 1 kilogram of water is just a water bottle, a big water bottle. That's a lot of joules involved, okay? Yes, which means this line is gonna be longer. Anyway, why am I discussing this? I'm discussing this to just let you feel the order of magnitude of the different heat, to make you understand why I'm using MC delta T, to make you know that it's only related to the change in temperature. Also, that change in temperature and change in phase do not happen at the same time. They happen one step at a time. However, for our experiment, we're gonna do MC delta T only. We're gonna take water at room temperature and heat it up to something like 40 degrees. We're gonna take a solid at 90 degrees and cool it down to 40 degrees, and that's it. No melting, no evaporation. However, we have something interesting. We're gonna do thermal equilibrium. Thermal equilibrium. Can anyone explain this example of your daily life? You can unmute yourself. I would love to hear you. Even if you are in a coffee shop and it's loud, it's okay. It's not like my house is quiet. So unmute and talk. Let's talk. So what do you see in this picture?
So there will be a transfer of heat from the hot coffee to the cold milk, okay. And we will reach a temperature, a certain temperature.
So this is hot coffee and this is cold milk, and heat is transferred from the hot to the cold, and they reach a certain final temperature. That's thermal equilibrium, right? Rome is saying adding milk to coffee every morning. Yeah, they will reach an intermediate temperature. Ali is saying intermediate. And what do you mean by intermediate, Ali? Why do you want to call it intermediate? What is intermediate?
It's like a halfway point.
Okay, so Ali is saying it has to be in the middle. Is that exactly?
Not in the middle, exactly.
In between. So if this is T1, this is T2, T final has to be in between, not exactly the middle.
Yes.
It depends on what? Who decides, I mean by who, which parameter, decides T final? Rome is saying quantity. The quantity of who?
It depends. If we put more milk than coffee, then it would deviate more towards a colder temperature than a hot one.
Obviously, yeah, this is simple, like cooking 101. the more milk you add, the colder it's gonna be. So it is related, you mean by quantity, Romy and Carl and Roy, basically the mass 1 or mass 2. Anything else is related to? Water's temperature will barely change, but the other liquid's temperature will significantly change. Thank you, Jana. I love this. I love this. Water is, I call it very lazy, like it has a big inertia, but we're talking mechanics here. I mean by that, if you put water with any other solid, water is gonna be really lazy to change its own temperature. So even if it's a bit of water, the intermediate temperature Ali is talking about would be closer to the water's temperature, because water itself is gonna find it very difficult to change its temperature. So this example here is basically just a random example to tell you this is system 1, this is system 2. Heat will be transferred from system 1 to system 2 because system 1 is hotter. If system 1 and system 2 have the same mass, that's the first if. Another if is if they are the same sample, we're talking about water and water, so same specific heat and same mass, the T final is gonna be 50 degrees C. Karen said something very interesting. She said how far apart the temperatures are. So let's say they are 0 and 100, or they are 10 and 90. And we're still talking about the same sample and same mass. Isn't the final temperature will always be and remain 50 degrees C? And the question is for Karen. So the far apart, like the gap is 80 only. Here the gap is 100. How far apart temperature makes any difference, Karen? Probably I did not understand. What do you mean?
Yes, I meant if they were, for example, 0 degrees and 50 instead of 100.
Okay, so T final is gonna be affected in general, you mean? Isn't it gonna be the middle always if you're talking same mass, same specific heat? All right, so probably, yeah. So I'm gonna follow Maria's method. I'm gonna take Q gained and Q lost and make them equal, because heat is gonna get exchanged between system 1 and system 2. So system 1 is gonna lose Q and system 2 is gonna gain Q, same and equal and opposite. And this is an example we can try, very easy example just to make sure you got the idea. So we have a 2 kilogram piece of metal, we have the specific heat, and we have the temperature. Okay, I will get back to you, Jana. And then we have another example where we have another piece of metal, another specific heat, and another temperature. And what we want to do is find T final. We know that they're gonna reach the same T final, and we know we can use that Q1 is equal to minus Q2, or the heat is gonna be equal and opposite. Before we start doing the problem, I'm gonna read what Jana said. She's saying if we add 10 milliliters of liquid 1 and only a few drops, it will be closer to liquid 1 temperature. So it goes back to the quantity. Yes, that's true, Jana. Quantity is very important. However, don't forget that specific heat capacity is also important. Sometimes by adding a small quantity of water is going to give you a big change, because water by itself is not going to heat up easily or cool down easily. So the final temperature is usually closer to the one of water, because water takes a lot of time. Okay, it's like, just imagine water to be this very slow child, and it's gonna slow down all the family, in a way. All right, so I need a volunteer to help me write the given for this question. Like we know mass here and specific heat and temperature 1. Let me call it temperature 1. Okay, trying to scroll. And I want mass 2, C2, and temperature 2. What's temperature 2? Yeah, how do you find it? So temperature 2 is the initial temperature of metal 2 before you put them together. It is 80. Thank you, Carl. And 80 degrees C. All right. We need to do Q is equal. Yes, Romy, I see you. MC delta T. How do we find T final? Any thoughts? My job is to find T final. So T final equals question mark. How do I proceed? I have two solids in touching each other, in contact. All right, don't forget to do a minus, Maria. So I'm gonna take 2 times 1,000. I am writing slowly because of my trackpad, into T final minus 20 is gonna be equal to negative Q2, which is 3 times what's C? 1,500 times T final. We always do T final minus T initial, which is 80. Yes, you mean Roy MC delta T. Carl, I love your method. I'm gonna talk about it in a moment. Anyway, I am gonna be quiet for a second to calculate T final. How about you do the same? What would be T final? Just expand and solve for T final. I will be quiet for 1 second. No, 3 minutes. So far, waiting for your answer. I can see some answers in the chat. I don't know if anyone agrees with Carl. 1 extra minute. I have an answer as well. I just got it. I will share it with you in a moment. شو هالكارل هيدا مش عم لحق لك. Imagine Carl. We're gonna meet one day and I will never ever recognize you. How crazy is this? Jenna is giving out the same answer. Marilyn as well. I got the same answer, so I'm gonna simply write 62. I need units, please. Degree C. Perfect. All right, I'm gonna go back to Carl's method. I've been using Q1 is equal to negative Q2 or the opposite for a long time with my students, my IB students, until I realized that sometimes you have 3 objects in contact. And here you have to realize which ones are losing heat, which one are gaining heat, for you to be able to put the gaining heat on one side of the equation, the losing heat on the other side of the equation. And sometimes one of the substances is ice, and ice is basically raising its temperature, then melting, then raising the temperature again. So to find Q of heating ice to water at a certain temperature, you need to use MC delta T, MLF, then MC delta T, and it was really hectic. And then I realized that this is not a good idea. So Q1 is equal to negative Q2 is not a good idea. We'd rather, and this is like an advice from me, use Q1 plus Q2 is equal to 0. I know this sounds trivial, and you're saying شبه جسيمة, it's the same exact thing. Yes, I know, but if you end up with 3 objects, you wouldn't know where to put Q3. However, Shojana, what Roy, actually Carl said, he said Q plus Q equals 0, and we were doing Q is equal to negative Q. In case you end up with 3 objects, you wouldn't know which is negative, which is positive. So you'd rather put them all in one equation, Q1 plus Q2 plus Q3 equal to 0, okay? It will make your life so much easier. You don't have to do any estimation or expectations to know what to, because you don't know what T final is. Sometimes you can guess T final, okay? Probably when I talk about the experiments, I will ask you to guess T final. This is our experiment. It is very simple, 2 objects only. I have a hot metal, probably copper, probably tungsten, probably steel, and I'm talking about an easy cylinder. Before I start my experiment, I need to heat up my metal. I need people to give me ideas about how to heat up a metal. How do you heat up a cylinder of copper? Ideas, please. Place it in hot water. Yes, we're gonna do that. Any other ideas? Heat up a cylinder of copper. Heat up any object. I love hot water because it's gonna be homogeneous in a way, but if you heat up your solid on fire directly, Jana, yeah, probably it's not gonna be homogeneous. But however, I believe in conduction. It's like heat conduction is gonna be everywhere after a while, and same with hot water. So probably both are legit. However, probably heating a metal on fire directly would create some dirt on it, you know, not dirt, but I mean some, probably it's cleaner with water. I don't know. Anyway, heating your metal is not, a residue, is not part of the experiments. We're gonna heat the metal before the experiment. So please don't get confused, because I know for a fact that students on the benches, like back in the days when we were in the lab, they used to get confused. They thought heating the metal is step 1 of the experiment. No, heating the metal is step -1, like we do it before the experiment. Now my metal is hot, and let's assume the temperature is 85. You're gonna be given the temperature later on. So your metal is hot and the temperature is 85 degrees. What do I have here? I have cold water that I'm gonna take it as tap water. Okay. By the way, I forgot to tell you that the mass of the cylinder will be around 200 grams. Don't take those values in your lab reports. I'm going to give you more precise values later. For the water, I'm going to measure 100 milliliters of water. How many grams is that? 100 milliliters of water. How many grams is that? Okay, 100 grams. And you can see it's half the mass of the solid. Water temperature, let's say, is 20 degrees C, room temperature. When I did the experiment in the video that I'm going to show you in a while, it was around 18. I can't remember actually. Yeah, probably 19, a bit below 20. The measurements that I'm going to give you may be a bit different. So I'm going to take 100 grams, 20 degrees C of water, 200 grams, 85 degrees of copper. Put them together, reach T final. Can you guess what T final would be? Do you think it's gonna be exactly in the middle, or closer to 20 or closer to 85, and why? We're trying to guess. It's a guess game to see if it makes sense to you, to see if the conceptual understanding of you is good. It will be closer to water. This is what Ali said, and Roy said, and Carl, and Maria. However, and Jana. However, isn't water half the quantity of the metal? It depends on C, Romy, and we know that C of water is the biggest. That's why everybody said T final is closer to water, because it has a higher C. All metals, if we go back to this example, all of them, silver, copper, they have specific heat capacity much smaller than water. So my question for the students who said T final is closer to water, isn't it that water is half the mass of the copper? Don't you believe this will create a change in your answer? Even if it surrounds the metal from all sides, this means it's a good final temperature. By the way, everything is put in a container that is insulated and in calorimeter, so nothing is gonna escape to the environment. So again, T final, will it be closer to 20 or 85? You should take into account that water takes a lot of time to cool down or heat up, but also you should take into account that I'm having half the quantity of water, like only 100 grams. However, I have 200 grams of the metal. and they are surrounded by each other because thermal equilibrium is going to happen, like everything is going to be homogeneous, and that's a good thing, Jana. So do you still say that T final is going to be closer to 20? Closer, I mean between 20 and the midpoint of 20 and 85. So how do you account for the different C and the different mass? Any answer? Shall I repeat my question? So Romy is saying still closer to 20. Can you convince me, Romy? Can you unmute yourself? Why? However, the mass is different. How come it's still closer to water?
The mass of the metal is double the mass of the water, but the C of the water is more than double the C of the metal.
Thank you so
That's
much.
why it could be closer.
Thank you so much. It's not only greater than double. I was doing it with the other students. If we assume that this one is 0.4, the copper, and water is 4, it's like 10 times bigger. For the final temperature to be exactly in the middle, you need a mass of copper to be 10 times bigger for that of water, for both to be in equilibrium in a way, you see? So doubling the mass of copper is not enough to create T final in the middle. You see what I mean? So yes, T final is gonna be somewhere around 25 degrees C or 27, I can't remember. And you're gonna be surprised, it's too close to 20. يعني أنجأ حسيت it might be any change. أنجأ, it's so blind to the change in temperature, to the heat added to the system. All right, so that's it for our experiment. We're gonna take copper, we're gonna take another metal, do 3 trials for each. Why not 3 different metals? Because the experiment is time consuming. You need to heat your metal and wait for T final. T final is not gonna happen in 1 second. You need to wait around 4 or 5 minutes and more for the final temperature to stabilize, and do 3 trials of each, and you end up with 6 trials in total, if each of which will take 15 minutes. That's 90 minutes only taking measurements. So yeah, let me show you the lab report quickly. You will be asked, just a second, because this app was not active. Okay, now, okay, so you have metal 1 and metal 2, trial 1 to 3 for each, mass of sample 1, mass of sample 2, temperature sample 1, temperature sample 2, T final, and then you need to calculate C of the metal. 3 trials, you find the average. Then you repeat for C of metal 2, you find the average. C of the metal is known, like copper is known. You compare your experimental answer to the theoretical answer, and that's it. That's the lab report. It's so short. Now for the values, in the other group, they took a screenshot of the values. However, that's tentative. I wanted to change them, but I will not, because I'm not happy the uncertainties were given to you, but I will not change it. So if you want to take a screenshot. Also, the other group were asking me about T initial of the sample, which is not here. So we need to assume that T initial of the sample is equal to 100. I mean, I'm gonna put my solid, I mean the copper, in boiling water and wait a bit. So I'm gonna assume that the temperature of copper in boiling water is 100 degrees C. We did the experiment and it was like 99 degrees C, so 100 is a perfect estimation. Okay. However, in the lab, many students added a row and found the T initial of the hot solid, which is easy to measure, and it's usually 95. Sometimes you don't want to wait for the water to boil. Probably wait until you reach 85 and stop the heating process. Let me show you the video. It's still here. I'm not gonna, it's a short video, I know. I will simply go fast forward. This is the steam generator. I'm gonna use it open just to boil water. I will put the power of it to max because I don't want to wait. This water that I have here will not take part of the experiment. This is not sample 1, not sample 2. I'm repeating this because I know this is a major confusion for the students who were in the lab. This is a thermometer just to monitor the temperature of the water. These are the samples, 3 samples. I'm gonna only pick 2. Tungsten is the big one and copper is the small one. Okay, so this is the steam generator, water inside. It's dirty water, by the way. or not so dirty, but I mean like tap water. I'm gonna put it on, put the heat on max. The temperature was around 40, not 100 degrees yet. I'm gonna take one sample, okay? Probably pick the small one because it's experimentally easier to handle a small one. You see the wire hanging from it? It's only to make it easier for me to remove it. Otherwise, I'm gonna burn my skin. And trust me, this is not a very safe experiment. This is the calorimeter, which is basically a foam cup, and trust me, it works so well. Roy is asking, if we assume T initial as 100, it would be a source of error, right? Yes, any assumption, Roy, is a source of error. Even if it's an excellent assumption, it makes my experiment not super precise. So it decreases a bit the precision, but yes, it's a source of error. Thank you for saying so. All right, so I'm gonna mix everything inside my calorimeter. I mean by everything, system 1 and system 2. Again, system 1 is cold water, system 2 is hot solid. And boiling water will not take part of the experiment. This is the cold water. You see 100 milliliters, and you can see the smallest subdivision divided by 2. So 100 milliliters is also not very precisely measured. Okay? So yeah, but it is an excellent estimation. I'm not saying it's bad. So I'm gonna measure the temperature of it. It's 19.5 probably. And I'm gonna put system 1 in my calorimeter, ready to receive the hot solid. I'm still waiting for my solid to heat up. Yes. Probably it reached a value close to 100. This is 100. So now I'm gonna remove my system and put it inside the calorimeter. See, I'm removing it. I'm gonna put it inside. Oh, the simple act of removing my solid is gonna cool down my solid. Since we're talking about solids of low specific heat capacity, so we know that it's cooling down and heating up quickly. So this is also a source of error if you're writing them down, Roy. So I'm gonna put the solid directly in the water and close the calorimeter as fast as possible. If I'm slow, heat is gonna go to the environment, and that's a source of error. Also, the calorimeter, even if it's an excellent insulator, it has some limited insulation. Nothing is perfect eventually. Close it well. I know for a fact that closing it, this act is not very important. You can simply close it without screwing the lids in. Wait for T final, and by wait, I really mean wait few minutes, because the temperature is now 20. It was initially 19, it went up to 21. It's heating because of the hot solid. I think it's gonna reach 25. That's T final in my case. Like, we waited a lot. That's 23 now, 24. And now it's close to, it's not visible, 27, is it? Is it visible? Anyway, you don't need this measurement, but I would love to see what it is. Okay, I want to see. Okay, let me click play.
Then this will be your T final. T final is the...
Mashi, it's here. Like, it's not 25 yet. So you see, it was increased from 19.5 to 25 only, and the solid was 99 degrees. So nothing, not even reaching 30 degrees. And I'm repeating the experiment now for copper. So I did it for steel and then for copper in the video, but for the experiment itself, you have results for tungsten and copper. Tungsten is the big one. Okay, let me show you these results. They started with cold water. We did this experiment in the spring, I think. I don't know, but it was really not too cold. And then when they did trial 2, apparently the water was already hot. They did not wait for it to cool down, and it's okay, because whatever you start with, that's a good T initial. And then you see it's heating up with every trial, and that's good, because we don't want to waste time to wait for it to cool down, which means we don't need a big range of change. Why? We don't need it. T final is going to be affected by T initial of water, obviously. Yes, we don't need this. T total, the mass total, who cares? Mass of the calorimeter will not be taken into account, because we're going to assume that there is no change in the temperature of the calorimeter. That's an assumption also. So calorimeter takes a very small part of the experiment. We're ignoring it. So that's it. The lab report is very short and easy. And the experiment is over. And I'm gonna save this under your name. We'll send it to you along with the results and the experiment, the link to the experiment. And you can go unless you need me, you can stay. I will upload this to YouTube as soon as possible and send you the link. That's it. Cheers for spring of 2021. We're done with the experiments only. We can meet again anytime you want. I took the vaccine yesterday and my arm hurts a lot. I cannot lift my hand, my arm. No, not Sputnik. Thank you, bye. Yes, the arm is sore and I had fever over more than 24 hours. Thank you, Jana. Bye, everyone. We're not done yet, Carl, so we're gonna meet again. And please let me know if you have questions, okay? Meanwhile, I'll be correcting your lab reports. Hopefully now I can go a bit faster. All right, so Marilyn, no need to join during the exact timing of our labs. However, we can meet if you want us to. And if you want to target meeting during the time of our session, it will be awesome for you and for me because we're both free during this time. So during our session, I will be offline correcting your lab reports and I can answer your questions and we can meet directly, okay? Or we can meet on a different timing if you want us to. But we don't have live sessions anymore. But please do visit anytime you want. Just let me know.
Doctor?
Yes, you can do a lab 10 before lab 9, Carl, of course. Yes, Maria.
I wanted to make sure of the uncertainties of the ohm meter and the dial gauge.
Okay.
Because
okay, easy. Listen, both are digital measuring tools, right?
Right.
So whatever value you are given, the uncertainty is the smallest subdivision. خلصت. Very easy.
Okay, I put it as 0.01.
Yeah, if you are given 2 decimals, yes. And don't forget to add the unit because the unit count a lot. Anything else? All right, I'm gonna stop recording. I totally forgot.